get started. Everybody's kind of piling in here. So today we're lucky enough to have Dr. Allison Wing from Columbia here to present. A little bit of Allison's background. She did her undergrad at Cornell in atmospheric science, finishing in 2008 before she moved on to continue her studies at MIT under Carrie Emanuel, working mostly on tropical cyclones, cyclogenesis. And now she is an NSF AGS postdoc at Columbia. Her research kind of, as we'll see today, covers a variety of topics related to tropical convection and tropical cyclones. So with that, I'll just let her get started.
Everyone can hear me? Great. Okay. Thank you so much, Kevin, for inviting me. I'm really happy to be here. Despite growing up in the New York area, I've never made it out to Stony Brook before, so it's nice to be here and see the university and meet some people here. So as Kevin said, today I'm going to talk about the organization of tropical convection, some work I've done on self-aggregation, and then how that relates to tropical cyclogenesis. And this is work I've done in collaboration with Carrie Emanuel, Tim Cronin, Susanna Camargo, and Adam Sobel. And so a somewhat simpler title for this talk would be cloud systems in the tropics. And so to motivate it, I'm going to show this satellite animation here. So this is just from the GOES satellite. It's just the 2 full disk images over about a week-long period in September 2012. And I just want you to focus on the kind of convection going on, the cloud systems in the tropical belt here. And the movie's about to finish, so I'll play it again. But you'll notice that the clouds tend to be organized into clusters, this sort of mesoscale clumping of convection. And so this is what I mean when I'm talking about organized tropical convection. Sometimes we have things that turn into hurricanes, as we did here. I think this cluster is going to form a hurricane in the East Pacific. We've got another one here, some other clusters along the ITCZ, as well as over land in the tropical land masses. So convection in the tropics, clouds in the tropics, like to clump together. So are these tropical convective clusters important, and why are they important? Well, as we saw in the movie, they occur across a range of spatial and temporal scales, and therefore are responsible for a great deal of the rainfall and cloudiness in the tropics, with estimates putting about 50% of tropical rainfall as being due to organized convective systems. And so this allows organized convection to modulate the radiative heating and cooling rates of the surface and atmosphere, and therefore influence the large-scale circulation and moisture distribution. So understanding how and why convection organizes is important for understanding both tropical and global climate and climate variability. Additionally, as we saw in that satellite animation, sometimes these cloud clusters turn into hurricanes, like this one in the satellite image here. Globally, about 6.5% of tropical cyclones form hurricanes each year. And so an understanding of convective organization more generally is tightly linked to the problem of tropical cyclogenesis, which remains one of the largely unsolved problems in tropical meteorology, with, for instance, no theory governing the frequency of tropical cyclones occurring globally in each year. And additionally, understanding this sort of mesoscale organization might be relevant to understanding convective organization on a larger scale, such as for the Madden-Julian oscillation. So the MJO is a planetary scale, 30 to 60-day oscillation of convection and precipitation that propagates across the Indian and Pacific Ocean. And as it does so, it has a direct impact on local weather, modulates tropical cyclone activity, and through teleconnections also can affect weather in the mid-latitudes. But despite its importance, a complete theory for the MJO remains elusive. So any sort of insights we can gain onto the mechanisms of convective organization could help us understand the MJO better as well. So the approach that I take in my work to this problem is to perform idealized modeling of convective organization in radiative-convective equilibrium using a cloud-resolving model. And the goal of my work is to improve our understanding of mechanisms by which convection organizes. And so just so we're all on the same page as to what radiative-convective equilibrium is, these are all the components of it. We have shortwave radiation coming in from the sun that heats the surface and atmosphere. The surface then cools by emitting longwave radiation, some of which is absorbed and re-emitted by the atmosphere. And we have net energy balance at the top of the atmosphere. Now, if that was the only thing that was going on, the atmosphere would be unstable and therefore start to convect. And so then we have turbulent fluxes of latent and sensible heat from the surface to the atmosphere. And as that air rises, it cools and condenses to form clouds and precipitation. And so what radiative-convective equilibrium is a statistical balance between the net radiative cooling of the atmosphere and the convective heating by these rising warm, moist air parcels. And it's a pretty good first-order approximation for the tropical atmosphere. And so that's the framework we're going to use here. And then I'm going to be performing some cloud-resolving model simulations. And in this talk, I'm going to describe 3 different sets of simulations that I performed. They have broadly the same setup, so I'll just kind of describe it in detail here first. The cloud-resolving model that I use is the System for Atmospheric Modeling, or SAM, written by your own Murat Karatanov. And we're going to use a box situated over an imaginary patch of the tropical ocean. And so for this first set of simulations, it has a domain size of 768 kilometers in the 2 horizontal dimensions, with a horizontal resolution of 3 kilometers. And so it's really more of a cloud system resolving model. In terms of the boundary conditions, it has periodic lateral boundaries, so what goes in one side comes back out the other. The lower boundary condition is just a fixed, constant sea surface temperature. I've done this over a range of temperatures, but the first simulations I'll describe were at 305 Kelvin. And at the top, we just have a rigid lid with constant solar insolation. Now, the important thing about this setup here is that the boundary conditions are completely homogeneous. There's no gradients imposed or allowed to develop. And there's no external forcing. There's no mean wind. There's no imposed vertical velocity or anything. The only convective organization that can happen in this kind of setup is something that results from interactions between the convection and its environment. But importantly, in that regard, we have fully interactive radiation and surface fluxes. And in this first set of simulations I'm going to describe, there's no rotation. Later on, we'll add the rotation back in. OK, so what happens when we take a model like this and run it to radiative-convective equilibrium? So here we're looking at one of these simulations. It's a top view. We're looking down on the simulation. The gray and white shading are clouds here. It's just an isosurface of cloud condensate. And the colors are water vapor mixing ratio near the surface. And so you can see that the convection is kind of occurring randomly in space and time, a bit like popcorn popping in a pan. But you'll notice that there's this kind of patch here where we don't have any clouds and that the near surface humidity is less. And so this dry patch over time gets drier and grows to expand to actually force all the convection to become increasingly localized. And so in this situation, instead of the convection continually to be distributed randomly, it aggregates into a single clump. And as this occurs, the moist regions where the convection is get moister at the expense of these drier areas here, which get much, much drier. And so this process is known as self-aggregation, which is a spontaneous transition from randomly distributed to organized convection despite completely homogeneous boundary conditions. And by this definition, it occurs in a variety of idealized numerical simulations, from cloud-resolving models like this to even global models with convective parameterizations. So what I'm interested in doing is really understanding the mechanisms by which this transition occurs and quantifying them and then seeing how they affect different things. And so once it gets into the state where you have this one single cluster of convection, it happily stays there for as long as you run the simulation. Now, one other thing,
yeah. Can you ask a question?
Sure.
Yeah, I just want to know what kind of scales are you really interested in, focused on? Because when we look at the satellite picture, it seems that there are different scales. There are some really big blobs, and there are sort of smaller clusters. So what sort of scale?
So in these simulations, it's sort of a mesoscale size cluster that forms. It's order of, a few hundred, 100 to a few hundred kilometers. In some simulations I'm going to talk about later, this same process can occur on a larger, more planetary scale, order 1,000 kilometers. So I'm really interested in a range of scales, but yeah, at least mesoscale and up. Good question. So the other thing I wanted to point out by the simulation is that visually it looks just like a reorganization of the convection, but it's not simply just a spatial reorganization. It has important impacts on the domain mean climate. So in this left panel here, I'm just plotting a profile of relative humidity, both at the beginning of the simulation, before it's aggregated in the bold line, and then at the end of the simulation after it's aggregated. And so as you can see, the domain is dramatically drier when it's aggregated as opposed to disaggregated. I mean, these are relative humidities in the free troposphere of 20% or less. It's really, really dry. So this is a huge difference. And we see this to some extent in observations as well. And so this is from a study by Tobin et al. Who looked in satellite observations and reanalysis of the degree of aggregation in a given state and found that when it was more aggregated, it was drier in the free troposphere. And there were associated changes to cloudiness and radiative fluxes as well. And so this really expands the importance of this phenomena. We're interested in sort of the internal dynamics of it, but we also are interested in how it might feed back on climate. So it's potentially really important because of these big changes that occur as a result of the aggregation. Okay, so just to sort of outline the rest of the talk here, I've given some motivation and described the model simulations, and now I'm going to head into understanding what causes self-aggregation and what are the physical mechanisms. Following that, I'll address how domain geometry influences these mechanisms, and then relate it to tropical cyclogenesis before wrapping up with some conclusions. So again, the questions I'm asking here are what feedbacks are important to self-aggregation and what is their magnitude and what are the physical mechanisms behind each one of these feedbacks. Now, in that movie I showed, I mentioned that as aggregation proceeds, you have these dry regions that are getting drier and moist regions that are getting moister. So another way to think of that is that you have an increase in the spatial variance of your humidity. And so in order to quantify these feedbacks, we actually look at a budget for spatial variance. And we use frozen moist static energy here because that's a conserved variable in the model given by this equation here. So we just have the internal energy, the gravitational potential energy, the latent energy, and then subtracting off an ice term to make it frozen moist static energy. And we're going to be considering anomalies from the horizontal mean to give us our variance. And so again, why this budget? Frozen moist static energy is conserved in this model under both under most adiabatic displacements, including the freezing and melting and precipitation. And because we're considering a column integrated frozen moist static energy budget, its column integral is not changed by convection. Convection just redistributes frozen moist static energy in the vertical. And then, as self-aggregation progresses and the dry regions get drier and the moist regions get moister, the spatial variability of frozen moist static energy really just depends on this moisture variability. So this frozen moist static energy variance increases as self-aggregation progresses. And so using a budget for it allows us to then say, okay, which processes actually cause that increase in variance, and those are the processes that favor self-aggregation.
Just explain again for non-meteorologists, what's frozen moist static energy? How can energy be static?
It's just a measure sort of the net energy of a given atmospheric column at that time. And so it just is the internal energy, which depends on the temperature, so sensible heat here, the gravitational potential energy, which doesn't vary spatially because it's just, at any height, it serves as a function of that. Most of its variability comes from the latent energy, so how much moisture you have, because if you were to evaporate that, you would release that energy to change things. And then it just is frozen because in this particular model, the thermodynamic variable includes ice. And so in order for this to be conserved, we need to subtract off the contribution from freezing or melting of solid ice condensate. So it's a pretty standard thermodynamic variable. It's similar to moist entropy in how it evolves. In terms of the column integral, again, it really kind of just varies with the column integral of the humidity of the water vapor mixing ratio. But it's a really important sort of variable for any sort of instabilities or circulations that involve moisture in the atmosphere. And so if you follow around what happens to moist static energy, then that's going to tell you what is going on with your circulations and what's giving you these instabilities. So what are these different sources and sinks of frozen moist static energy? There are all of these terms here, but basically they all have to do with imagining sort of a column in the atmosphere and thinking about what can add energy to or take away from that column. And so the first things are radiation, so radiative heating or cooling of the atmosphere by either long-wave fluxes or shortwave fluxes. And so this is the shortwave flux convergence here, where we're just taking the amount of solar heating coming in at the top of the atmosphere, the amount that's coming out at the surface, and taking the difference between those two fluxes to think about the sort of heating of the column itself due to shortwave absorption. Similarly, for the long-wave term, we have the difference between the amount of long wave going out of the top of the atmosphere and the amount coming out of the surface to get the column long wave usually cooling. Okay, and so those are the radiative terms. We have shortwave and longwave here. And then we also have, at the bottom of the column, a surface enthalpy flux from the ocean to the atmosphere, which depends on the surface wind speed and the air-sea temperature and moisture difference. So this is just fluxes of sensible heat and evaporation from the ocean that are adding energy to the atmosphere. And so that's this term here, surface enthalpy flux. And then finally, we can have advection into or out of our column. That's this final term here, which is the convergence of the vertically integrated flux of convection. And so that's just saying if you have more air coming in, then going out, integrate that vertically and see how that transports the moist static energy into or out of your region. And so when we think about our budget, each of the terms in our budget is a function of an anomaly of frozen moist static energy, again from the spatial mean, multiplied by an anomaly in one of these sources or sinks of frozen moist static energy. And so if you have a region, a process that's increasing your moist static energy of an already moist region, then that's going to cause the moist static energy to increase there. It's going to become moister, more favorable for convection, and be a positive feedback on aggregation and on increasing this variance here. Likewise, if you have a process that is decreasing the frozen moist static energy of a moist region, that's going to be a negative feedback on aggregation. So it's all about, are the moist regions going to have their moisture increase, aka frozen moist static energy increase, as a result of these different processes, or not? Because we want to amplify any anomalies we have to give us that sort of separation into a dry region with no convection and a moist region with lots of convection. So the way that we actually compute this budget is we calculate each term at each grid point in time step in the simulation. And then when I show it to you, we've averaged over 1 day and then averaged over a 48 by 48 kilometer square block just to smooth things out a little bit and focus on some of these larger sort of scales of organization. And then because we're interested in sort of what's happening in these dry regions versus the moisture regions, we're going to actually sort everything according to the value of column relative humidity that each block has. And so that way we can look at what feedbacks are operating in the different parts of the domain. It's also sort of a way of taking 3 dimensions and turning it into one. So we integrated in the column to get rid of the vertical dimension, and now we're doing this humidity sorting to take our horizontal 2 dimensions and give it only 1. And then finally, because the variance itself increases over 2 orders of magnitude over the course of the simulation, at each time we're going to scale just by the mean of the variance, just to have a easier comparison between different sort of parts of the simulation. So with that, now we can look at what actually happens when we compute this budget. So there's a lot going on in this figure, and I'm going to show a few others like it. So let me explain. On the y-axis, we have time from the beginning of the simulation, day 0, towards the end, which is day 100. And then these images here are just snapshots of, well, I guess they're daily means, of the precipitable water, so just the column integrated water vapor, just to show you kind of where we are in the evolution of the simulation, if you recall from the movie. So at day 10, we have that small dry area starting to form. By day 30, it's gotten much bigger and stronger. By day 60, we have this moist band where all aggregation is, and then at the end of the simulation, we have one single circular cluster. And then on the x-axis, we have our moisture space, and so this is horizontally regions that are dry and regions that are moist. The black line here is just where our anomaly of frozen moist static energy from the mean is 0. So you can think of it as being everywhere to the left of the black line is drier than average, and everywhere to the right of the black line is moister than average. And then what's plotted in the colors is, in this case, it's the sum of these 3 diabatic feedback terms, the radiative flux convergences and the surface enthalpy flux feedback terms. And really, I just want you to focus on if it's red or if it's blue, and how red or how blue is it. And so that's telling you if it's a positive feedback or a negative feedback. And the units are a rate, so it's sort of how a sort of non-dimensional rate of change of the frozen moist static energy with time. So you'll see that we have really strong positive diabatic feedback in the dry regions at the beginning of the simulation, again indicating that this is beginning as a dry patch that forms and then amplifies and expands. We also have very strong positive diabatic feedbacks at the end of the simulation in the moistest regions, which are right at the center of our cluster here. the other thing to notice here is that in the dry regions, sort of from day 30 to 60 or so, some of the diabatic feedback is actually negative. But if you compare sort of here to here, the dry regions, the driest regions of the domain, are still getting drier during that time. And so that's telling us that during this time, it's actually the other term, the advective term, that is contributing to enhancing those anomalies. Okay, so now we can break it up into each piece. And we start with the surface fluxes, and the surface enthalpy fluxes are written in terms of these bulk formula. We have latent heat flux and then the sensible heat flux. And they just depend on the wind speed and then this air-sea difference in humidity and temperature. And so we can partition our surface flux anomalies into a part due just to the wind speed variations, a part due just to the variations in temperature and humidity differences, so this air-sea enthalpy disequilibrium, and then an eddy term that's due to the covariance of those two anomalies. So starting with the part of the surface flux feedback due to the variations in the wind speed. That picture looks like this. So again, we see mostly red, so it's a positive feedback on aggregation. Strongest in the dry regions in the beginning of the simulation, and then sort of at the periphery of our cluster when it's maintaining it. So why is this a positive feedback? Well, this is just a snapshot from the end of the simulation. So we have our cloud cluster here. And what's in the color shading is just the magnitude of the surface wind speed. And you'll notice that it is larger near the cloud cluster than it is in these drier non-convecting regions. And this is what's known as the wishy feedback, wind-induced surface heat exchange. So because you have stronger wind speeds in the moistest columns where the convection is, that will be enhancing the convection there, increasing your moist static energy, and acting as a positive feedback on aggregation. Now the interesting thing here is that while this surface flux wind feedback is a strong positive feedback, it's largely counteracted by the other thing that affects the surface fluxes, which is that air-sea enthalpy disequilibrium. And so the surface flux feedback due to the variations in the enthalpy disequilibrium is a really big negative feedback, as you can see here, just basically blue everywhere. And so what causes that to be a negative feedback? Well, going back to our snapshot here, now I'm plotting the actual air-sea enthalpy disequilibrium. And since we have fixed sea surface temperature in this simulation, that air-sea enthalpy disequilibrium really just depends on what the boundary layer humidity does, so the air humidity near the surface. And where we have our clouds and convection, the entire troposphere, including the boundary layer, is more humid than it is elsewhere in the domain. And so that is going to cause our air-sea disequilibrium to be suppressed in that area compared to elsewhere, which, all else being equal, will then act to suppress the surface fluxes here. And so we can add this sort of to our list of negative feedbacks. And so the effects of wind on surface fluxes and the effects of the enthalpy disequilibrium on surface fluxes are opposing sort of feedbacks. And if you add them together, we find that there's a lot of cancellation between the two. And this is the picture we get for looking at the total surface flux feedback. We see that it's an important positive feedback in the beginning of the simulation, but then it switches to become a negative feedback for most of the rest of the simulation. And so it's sort of interesting that its role changes with time as aggregation progresses. Okay, so now how about the radiative terms? So starting with the shortwave term that's shown here, and again you see that it's red, but it's not as bright a red as the other one does. And so the shortwave radiation is not as important as the surface fluxes. It's a smaller feedback, but it is the same order of magnitude, so it's not negligible. We do have to think about it. And when we want to know why this is a positive feedback, it's a fairly simple explanation. And you have to remember that here, these shortwave, in general, the radiative feedback, but this is talking about what's happening to the shortwave heating of the atmosphere itself. So it's not a feedback on surface temperature or on the top of atmosphere budget. It's the feedback on what the column is doing. And so if we plot our column averaged shortwave heating rate in the colors here, we find that it's much smaller in these dry, non-convecting areas than it is in our moist convecting areas. And this is simply because water vapor is a big absorber of shortwave radiation in the atmosphere. And so where you have more water vapor, you're going to have more shortwave heating, increase your moist static energy, positive feedback on aggregation. You also notice that in the center of the cluster where we have all these clouds, our shortwave radiative heating rate is reduced here, and that's because these deep, thick clouds, as the solar radiation comes in from the top of the atmosphere, is being reflected off the top of these clouds before it can penetrate into the atmosphere, where it could be absorbed by the moist air. And so you actually get a reduction in your shortwave feedback right in the very, very, very moistest columns in the center of your cluster. So we can add shortwave to our list of positive feedback. So then the last one is long-wave radiation, which is kind of complicated. As you can see, there's a lot of both red and blue on this plot here. Very strongly positive in the dry regions at the beginning of the simulation, but then it switches to being a negative feedback. It's also a very strong positive feedback in the moist regions at the center of that cluster, maintaining the aggregated state once it exists. And so you might ask yourself how much of this is due to clouds versus clear sky processes. So to answer that, we can compute the same term using just the clear sky fluxes. So we calculate what all the long wave heating rates should be as if there were no clouds at all. And this is what we get when we see that. And so I'll flip back and forth between the two. So we have total clear sky, total clear sky. So the first thing that jumps out to me is that this big positive anomaly, or positive feedback here, is mostly missing in the clear sky. And so that's telling us that this is really a cloud feedback here. And it's simply anvil greenhouse warming. You have all these thick, high, deep clouds that are absorbing a lot of the long-wave radiation emitted up from below and heating the column. But in the beginning of the simulation, in the dry regions, actually a substantial portion of our long-wave feedback is due just to clear sky processes. And even these clear sky processes become a negative feedback as time goes on. And so we need to explain what causes this long-wave feedback to actually change sign. And so in order to do that, I'm going to sort of do a thought experiment here where we consider the behavior of long-wave fluxes in a simple two-layer representation of the atmosphere. And so don't really worry about all the equations, just the key thing is that we have the surface, which is emitting long-wave radiation, some of which is absorbed by the layers above it, some of which is transmitted through out to space. We have the lower layer of our atmosphere, which absorbs both up and down. And then we have our upper layer of our atmosphere, which emits and absorbs radiation both up and down. And you can just take this and write an equation for what the net sort of long-wave cooling is, summed up over all the layers. And so what happens if we, say, start to dry out the atmosphere, as occurs in the beginning of aggregation? So if we start to dry out the upper atmosphere, because water vapor is the greenhouse gas, it's a big absorber and emitter of long-wave radiation, decreasing our water vapor is going to decrease the upper level emissivity, which is this little epsilon guy here. And so because we've decreased the upper level emissivity, then this upper level is actually going to be cooling to space less than it was before, just because there are fewer emitters there. However, it's also going to be, so the radiative cooling of the upper troposphere is decreasing because of that. But the upper level is also going to be emitting less to the layers down below. And because this upper troposphere has less water vapor, it's more transparent to the radiation that is emitted from the lower troposphere and the surface. And so those layers are going to actually lose more energy to space. And so in total, the lower troposphere is actually going to have increased radiative cooling. And so you have these two opposing responses because of both the local and remote effects of radiation. The upper troposphere is cooling less, but the lower troposphere is cooling more. What happens when you do the column integral of that? It's not immediately obvious to me, and probably isn't to you either. But if you take some numbers and put them in here, you can find the answer. And you can find that, well, it depends. It depends on what your emissivities were to start with, meaning how much water vapor you had to start with, and then how much you change it, how much you dry it out. And so what happens is shown here. We have on the x-axis our lower level emissivity, and on the y-axis our upper level emissivity. In the beginning of the simulation, as those dry paths just starts to form, we kind of take this path here, and we have more cooling than we did before, therefore a positive feedback on aggregation. But as the dry regions get drier, we start to really decrease the emissivity in the lower troposphere as well, and follow a path more like this, causing us to have less cooling than we did before, and therefore switching to a negative feedback. And this is, as complicated as this is, only looking at clear sky clouds, as we saw, can complicate things a lot more, which I'll talk a little bit more about later. But this really interesting behavior of the long-wave radiation is, again, a result of the balancing of these local and remote responses. And it's really interesting that, depending on both your initial state and how you change things, you can get, a totally different sign in your response. So just to summarize this part of the talk, I've described a new analysis method that I've used to quantify the feedback governing self-aggregation. And we found that there are multiple feedback mechanisms working together to permit the convection to aggregate. So we had long-wave radiation, we had shortwave radiation, and we had the surface flux feedback. They all contribute at different times of the simulation. Some are stronger than others, but they all have a role to play. So now my question is, well, that was in this square box, where we have one single cluster that's a couple hundred kilometers in size. What if we have a different type of domain where we might have perhaps the potential for larger scale organization to develop or have more interaction between the convection and the large scale circulation? And so how does our domain geometry affect the mechanisms of self-aggregation? So this is the second set of simulations. And it's really the same exact setup as before using the same cloud resolving model. But all I'm going to do is vary the horizontal aspect ratio of our domain. And so we're going to go from having, before we had a square, so 1 to 1, and then we're going to go to aspect ratio of 4 to 1, 16 to 1, and 64 to 1. And so the easiest way to describe that is just to show a picture. And so these are our 4 different types of simulation. And what's plotted here is just the daily mean precipitable water, so just, again, the column integrated water vapor. And so you can see that we have some sort of aggregation occurring in all of them. And so this is like what we had before, one circular cluster. And then when we go to the 4 to 1 aspect ratio, we have these bands of these moist bands where convection is confined. Similarly, in our half channel, 16 to 1, and then our really long channels. This guy's 12,000 kilometers long, but only 200 kilometers wide. So it's really long and narrow. You can also see that the strength of the aggregation is stronger the more sort of symmetric our aspect ratio is. These moist regions are moister here than these guys are here. And so to focus on the mechanism, I'm just going to compare the two extremes, the square, which we had before, and the elongated channel here. Now, instead of doing this whole moisture sorting and looking at how things are evolving in that space, just to simplify things, I'm going to just show you the domain mean of our variance budget. So I'm going to use that same framework I described before on these simulations. And this is what we get. And so this is the square simulation, the one I just spent the last 20 minutes describing to you. But again, now I've averaged spatially for all the terms. And so each of the lines here is a different term in our variance budget. So we have in the blue our long wave feedback, in the red our short wave feedback, in the green our surface flux feedback, in the black it's just the sum of those 3 diabatic feedbacks, and in the pink we've got our advective term, the convergence of the flux of moist static energy. And on the left we have the same thing but for our long channel. And so what I want you to look at really is what's happening in the beginning of the simulation, because we're interested in what processes get this instability started. And they're really remarkably similar, I think. So if you look at, in both cases, it's the surface flux feedback, the green line, and the long wave feedback that are the largest. And their magnitudes are actually even very close between these two simulations as well. And so that's saying that the aggregation in this long channel simulation is really caused by the same mechanisms as it is in our square simulation. And so that's an important step to describing, determining if this process is really robust. However, there is a difference, and that's in this pink term here. Although you can't see it very well here, believe me when I say that it's positive during these intermediate stages of aggregation. Is that's during that time when the advection by the circulation is actually contributing to aggregation. Whereas in the channel, the advection term is always negative. It's always damping the anomalies. And this difference is whether you have transport of the moist static energy up gradient, as we do here, so moving it from the dry regions to the moist regions. Another way of thinking about it is that you have negative gross moist stability, or your overturning circulation is exporting energy, importing energy. Whereas in the channel, that circulation is always exporting energy. You're always transporting energy by advection from the moist regions, downgrading it to the dry regions. It's always damping the anomalies, and is not contributing to aggregation. And so, while people in the past have talked a lot about how advection by the circulation is important for aggregation, it's really not robust when you go to different geometries, whereas these radiative and surface flux feedbacks contributing in the beginning of the simulation are. They're really pretty much the same between the two simulations. So that's an important thing. And then the other thing that's useful about this channel geometry is that the aggregation occurs over a really wide range of temperatures. And so then we can take advantage of that and look at how these different feedbacks behave across this wide range of temperatures. And so that's shown here. So we go from 280 Kelvin, 285, all the way down to 310. So the one I was showing you before was this guy here, 305 Kelvin. And I just want you to focus on the two radiative terms. So starting with the blue line, which is the Longwave feedback. It was an important positive feedback in these warm simulations, but if we use a colder fixed SST, we see it's a negative feedback initially at these cold sea surface temperatures. And so we need to explain why that occurs. And then we can see that the shortwave feedback actually is sort of counteracting that. And so it's a positive feedback everywhere, but it's much, much stronger positive feedback in these really, really cold simulations. And it turns out that both of these effects, the negative long wave and the strong positive shortwave at the cold simulations, are actually due to clouds. And so why would we have these sorts of cloud feedbacks? They're a little bit counterintuitive. Usually for the long wave, we think of a positive long wave cloud feedback because all these clouds are absorbing long wave radiation that's emitted up from below and heating the atmosphere. But here we actually have a negative long wave cloud feedback, which means that where we have more clouds, we have actually more cooling than we did before. And I think the answer here is that in these really cold situations, 280 Kelvin, at the surface, that's really, really cold. Most of the atmosphere will be below freezing. You just don't have that much water vapor, and so your atmosphere is very optically thin. And so if you stick in a cloud, you're actually going to be increasing your emissivity because you're putting in more emitters of long-wave radiation. So just because you have more emitters means now you're actually able to cool the atmosphere more. So that, I think, is the answer for that. And again, because you'd have more clouds in the somewhat moisture regions, that's why it's a negative feedback. Okay, so how about this positive shortwave cloud feedback? Again, counterintuitive. Usually we think of clouds as reflecting shortwave radiation and preventing it from being absorbed, where it could be a positive feedback. And so there's a couple different ways that I think this could happen. One is that if you have more low clouds in your moist regions, this would actually increase the amount of reflected shortwave that goes back up into the atmosphere, where it has kind of a second chance at being absorbed. Or you could have just direct shortwave absorption by cloud water. Cloud water is also a shortwave absorber. Or we could have more high clouds that scatter the radiation, the solar radiation more, and give it a longer path length through the atmosphere and have sort of, again, more chances for atmospheric absorption. And so, I don't know which of these three methods is dominating in these simulations, but some combination of them. Okay, so that's what's happening in the channel simulation. We have these sort of interesting ways that the radiative feedbacks vary with temperature, which was exciting to discover. But at the beginning, I said that one of the reasons we were interested in this problem was because of tropical cyclones. So let's make this exciting and turn on rotation and see what happens when we take a model in radiative-convective equilibrium. Again, the same exact setup as before. No external forcing, fixed sea surface temperature, totally homogeneous boundary conditions, but we've turned on rotation. We've stuck it on an F-plane at 20 north. What happens? So I have to exit this briefly because the file is too big to stick in PowerPoint. But it's going to be worth it, I promise. Maybe. Come on. There you go. Okay. So again, we're looking down on the simulation. The white colors are clouds. The greens and blues are humidity. So yellow is dry near the surface. Blue is moist. And so it's sort of convecting everywhere at this point, but you see there's some areas where it's a little bit drier than others. But there's this kind of like growing moist area here that's starting to get moister and starting to spin up. And so phenomenologically, it evolves differently than a non-rotating case. And then all of a sudden, there we go. There's our hurricane. So in the non-rotating case, remember we had that one dry patch that kind of slowly grew and expanded to force all the convection into a single cluster. In the rotating case, it really is more of a moist blob that spins up. And so it's sort of a dichotomy in the behavior.
How do you make the hurricane stay in the middle of the picture?
It just, there's no mean wind, so it's not really going to move around except for how it advects itself. And as you can see, it did move sort of later in the simulation, but yeah, I mean, in the real world, there's no beta here, there's no beta drift, so we just have a fixed Coriolis value, and so, with no beta drift and no mean winds to advect a storm around, it should really more or less stay in the same place. But good observation. So, just to prove to you that this is a hurricane, and this movie's on my website if you want to watch it more later. It's pretty mesmerizing. And actually, if you come to Lamont to visit ever, we can show it to you in 3 dimensions, like put on 3D glasses and have those clouds really popping out of the screen at you. It's really, really awesome. Okay, so obviously from the movie it looked like a hurricane that formed spontaneously, again, out of just nothing, just initialized by random noise. And this is just to sort of show you the structure to convince you it really is a hurricane. These are all height, radius, cross sections of the storm. So here we have our azimuthal mean tangential wind. And so we have a maximum wind speed of about 90 meters per second. That's almost 200 miles an hour. So it's a really strong hurricane. And then we have our sort of upper level anticyclone at the top here. In terms of the radial wind, we've got inflow near the surface, and then outflow near the top of the storm. We have the strongest updraft, again, in the eye wall, close to the center. And this is a really strong secondary circulation. Radial inflow of like 40 meters per second here. That's huge. And then in terms of temperature, hurricanes, as we know, are warm core systems. They're warm in the eye, and this occurs in our simulation as well. So this is the temperature anomaly from the domain mean. And so you can see it's 20 degrees warmer in the eye than it is elsewhere in the storm. So very strong hurricane, has the expected structure. So it really is a real hurricane that forms. How did it form? Are the mechanisms that cause this spontaneous tropical cyclogenesis the same as what caused our non-rotating self-aggregation? So in order to answer that question, I'm going to apply my moist static energy variance budget again and see what happens. So on the right is our non-rotating aggregation that we've been talking about this whole time. It looks different than it did before because I haven't scaled it by the domain mean variance as I did before. So that's just why the scale is different and the evolution looks different. But focusing in on these sort of early stages, in the early stages of aggregation, remember it was the green and blue lines, the the surface fluxes and the long-wave radiation that were most important. Well, the exact same thing is true in our rotating hurricane case. And again, they're about comparable magnitudes, the surface flux and the long-wave feedback. And so this is saying then that initial development of a sort of moist blob and broad circulation, it really is these same radiative-convective feedbacks that were giving us the non-rotating aggregation. However, it doesn't stay the same forever. And so if you look later on in the simulation, you see that as our hurricane forms, this is kind of during the time period when it's intensifying, it reaches its peak intensity around 40 days. During that time, our surface flux feedback really takes off and becomes the dominant feedback. And this is just because of the very strong wind speeds that we get in a hurricane. You get, a huge surface flux feedback from that. Whereas in the non-rotating simulation, remember, our surface flux feedback on those plots, it switched from positive to negative as we went on in time. And so the surface flux feedback is much more dominant in the rotating case than in the non-rotating case. And then also point out what's happening with the shortwave feedback. In both cases, this red line here is positive throughout the entire simulation, but it's much weaker in the rotating case than in the non-rotating case. And so shortwave feedbacks are not as important to the hurricane as they are to the non-rotating aggregation. And I think that's because you have, in general, less of a difference between the moist and dry regions in the hurricane case, and so you just don't have as big a gradient in your shortwave absorption. And you also have clouds that occur over a sort of wider area in the hurricane case compared to the non-hurricane case. So the final thing I just wanted to mention is that this is suggesting that these radiative feedbacks, the long wave in particular, is still important to the hurricane. And so another way we can compare these two and then see how important that feedback is think about what happens if we remove it. And so to show what happens for that, here I have plotted, I don't know why this stopped working, just a PDF of the precipitable water, the column integrated water vapor, and then how that evolves in time. So here's our non-rotating simulation here, and then our rotating hurricane simulation here. And so the colors is just how many points have a permissible water of that particular value. And so they have kind of a similar evolution. You start off by, shifting to drier values of permissible water for a while, and then, as the hurricane spins up, as their cluster forms, we start to, have this more skewed distribution where we go to moisture values. But just note that in the non-rotating case, it gets really, really dry. 20 millimeters or so is the lowest, whereas in the hurricane case, it doesn't get quite as dry. But this long tail of the distribution out to the right goes much further in the hurricane case than it does in the non-rotating. So how does this distribution look different if we remove all the radiative feedbacks? So that's what's happening here. And as you can see, it doesn't really change for the first 80 days of the simulation. So that's telling us that it's not aggregating during this time, and we don't have a hurricane form until the very, very end of the simulation. Similarly, if we remove just the long-wave water vapor feedback, we again have nothing happening. It's just, a tight distribution. That means convection kind of everywhere for the first half of the simulation. And then later on, we do have a hurricane form, and we see that distribution widen. And so this suggests that radiative feedbacks are important and definitely help a tropical cyclone form, but they're not strictly necessary since, at the end, you do still get it to form even without these feedbacks. So perhaps not as essential as it is for non-rotating aggregation, but still substantially important. Okay, so with that, I'm going to end. And just to kind of quickly summarize what I talked about here today, I talked about the phenomena of self-aggregation, which is where you have this transition from unorganized to organized convection. And associated with that, you have these big changes in domain mean quantities. I introduced a means of quantifying the physical mechanisms of self-aggregation, and we found that the long-wave radiation and surface fluxes were the most important feedbacks in terms of instigating the initial instability. And then we looked at how that changed when we changed the domain geometry. We explored what happened in a really long channel simulation, and we found that there, aggregation occurred across a really wide range of temperatures, and that it was the diabatic feedbacks as opposed to the advective that dominate the entire evolution of aggregation, and that the cloud-radiative feedbacks were especially important at low temperatures in this long channel. And then finally, I compared non-rotating radiative-convective equilibrium with rotating radiative-convective equilibrium, and compared, our self-aggregated cluster to the spontaneous tropical cyclogenesis. So there was a little bit difference, as you saw in those two movies. In the non-rotating case, it's really this dry region that expands, whereas in the rotating case, it's a moist region that spins up. But in both cases, the surface flux and long-wave feedbacks are very important in the beginning. And so that's saying that, the instigation of tropical cyclone formation is really caused by the same things as this non-rotating aggregation. But as it evolved, surface flux feedback became the most important term in the hurricane case, whereas it didn't in the non-rotating case. And so just to kind of go back to the motivation for this a little bit and talk about some sort of future directions, I think one of the biggest potential impacts of this work is, how aggregation could affect climate feedbacks or climate sensitivity. Because you get this big dramatic drying of the domain when you have aggregation, that has the potential to, since it changes the relative humidity, has the potential to, say, weaken the water vapor feedback. And there's all sorts of questions about whether or not GCM convective parameterizations are able to represent this effect, and if not, should they? Should we make them? And in general, it would be good to have a better handle of these relationships between convection, moisture, and radiation in observation. As I mentioned in the beginning, a big motivation was the MJO, and there's some recent work that suggests that the MJO might actually just be self-aggregation on a beta plane. Some of the current theories for MJO describe it as a moisture mode, which is, again, meaning that what happens to moist static energy is what's important. And these same, surface flux, radiative feedbacks, cloud feedbacks that are essential for self-aggregation have been found to be important for the MJO. And then finally, obviously this is just the tip of the iceberg for how aggregation might affect tropical cyclogenesis or be relevant for it. And that's an area that I'm actively working on and interested in pursuing further. Thank you for your attention.
We have time for some questions. Jaime, go first.
Very interesting.
Thank you.
Have you compared the SST fixed SST sensitivity for the tropical cyclogenesis?
I've done it only at a few sea surface temperatures so far. Like that one I showed you, well, the movie actually was at 303 Kelvin. I've also done it at 305 Kelvin and at 301. And it seems to be very similar. It would be interesting to see if at those much colder temperatures where we, which we would generally think would not, allow for tropical cyclogenesis, if the aggregation can still happen in the rotating framework there. So definitely plan on doing that.
Yeah, I'm just thinking if we allow the SST to change, such as in the slab ocean, that will probably change the shortwave feedback in the meantime to the long, and also in the meantime to the certain fluxes.
Absolutely.
Probably change something.
Yeah, so as you mentioned, definitely I'd expect it to change the shortwave feedback, and you could have situations like cloud masking and stuff like that. In general, I would expect putting in interactive sea surface temperature as damping the instability, probably. I know one group at MPI in Hamburg who have done self-aggregation simulations with interactive SST, and they found that you still get aggregation even when you have like a slab sort of mixed layer ocean. And they found that the depth of the slab sort of just affected how quickly aggregation occurred or not. The deeper the slab, the faster it occurred, because the SSTs didn't, respond on as fast a time scale. I'm definitely interested in doing that, but the problem is the simulations become much more expensive because it takes a lot. I mean, again, it depends on the depth of your slab, but it takes a lot longer for them to reach equilibrium. I mean, these already take 100 days, so it's maybe like 3 times longer at least or something. The other interesting thing is, if you let the SST vary, you would think, and this does happen, if you, after it aggregates and it's, really dry throughout most of the domain. I didn't show it, but the domain average OLR like shoots up because it's so dry in most of the domain, so it's cooling a lot more or wants to cool a lot more. And so the SSTs would actually then decrease a lot after it's aggregated. And some people have thought that that might then get you sort of into this feedback loop where the cluster might fall apart as those SSTs decreased. It doesn't seem that it's easy to get that to happen. Once you have this aggregated state, it really is stuck there. There's a lot of hysteresis in the system, which I think is just because you have this massive difference in the radiative cooling between the really dry kind of radiator fin regions and the cluster itself, which in the vertical mean is basically there is no radiative cooling at all. And it's really hard to break that symmetry unless you add in vertical wind shear or something like that. And in fact, in the channel simulations, we do have some domain mean vertical wind shears that do develop just on their own, which does weaken the aggregation at the end of the simulation. So, and I think Marat Krasinov is actually looking at this problem now, how shear affects aggregation and has the potential to kind of change how it evolves. So.
Yeah. One more quick one. The second one about the MGO modulations.
Yeah.
MGO itself, or more like the propagation, not an advection term. So in your mechanism, I did not see any wave propagation because
right.
that will stimulate your convection. So yeah,
well, I think with the MJO, the idea is that these sort of feedbacks, these radiative surface flux feedbacks, would be your source of instability for the MJO. And then I think it'd be probably advection by the large-scale flow and advection by the wave circulation that would get it to propagate. I don't know if you're familiar with the sort of Sobel and Maloney moisture mode sort of theories for the MJO. So for there, they really have all these same feedbacks that give you the instability in their model as I've diagnosed here, but they do get a dispersion relation. And I think I forget what it is. Like you need to have things, in order to get eastward propagation, you need to have these feedbacks like in phase or not in a sort of a specific way. So yeah, I don't think in the context of models of MJO as a self-aggregation, the propagation part has really been investigated that much. I'm just thinking, so this paper I mentioned is by Arnold and Randall. It just came out, where they looked at SPCAM over an aquaplanet and then compared a non-rotating RCE version of it with one that had the full sort of spherically varying rotation. And that got an MJO, and they compared the moist static energy budgets of that to the non-rotating aggregation they got and found it was very similar. but they were looking at sort of just a composite MJO mean state kind of situation, not its propagation.
The MPI, I'm sorry, for the non-rotating case,
Yeah.
did you actually see the intensity of that hurricane? Does it agree with Carrier's MPI here?
Oh, I have not actually calculated the potential intensity, but it seems that this is with a sea surface temperature of 305 Kelvin, so it definitely makes sense that it's a very strong storm. I know other people have done similar types of simulations and found that it does scale pretty well with potential intensity.
Yeah, just back to one of your motivations. So one of the motivations is sort of a lot of cloud clusters becomes a hurricane, but it's actually a small minority of that. So in these models, a lot of times they spun spontaneously.
Right.
So what's your thought about what sort of limits the tropocyclone growth
in
real life?
Oh, in real life. Well, lots of things. I mean, this is basically the most favorable environment one could have for tropical cyclogenesis. You have a very warm, fixed sea surface temperature, so essentially an endless supply of moisture and energy. There's no wind shear at all, at least initially. There's no mean winds. There's no, subsidence regions moving through other circulations. Basically, there's no land. Yeah, the hurricane's not really moving. And so I think it's, not surprising that you get a hurricane to form easily, I guess, and become so intense and persist for so long. However, I will point out that it took 20 days maybe for a hurricane to start to form and 40 days before it reached its peak intensity. Whereas in the real world, maybe we'll have a depression around for a week maybe before it kind of gets its act together and forms a hurricane. But the time scale doesn't quite match. And so that kind of remains an open question, in the real world where, you can't just sit around for 30 days with the same conditions and wait to happen. How do these feedbacks still work?
Yes, sort of follow up on that. It's sort of similar to volcanic instability, though. It depends on how big the perturbations you start with initially.
Right.
Because volcanic instability, if you start with minute, very small noise, it will take hundreds of days for it to grow into a cyclone.
Right. So in the real world, it's a finite amplitude sort of phenomenon. You have these pre-existing disturbances. Where in here, I'm starting from, I think it's like 0.1 Kelvin is like my initial random noise. But you could think, okay, maybe the hurricanes are coming from existing depressions that are large amplitude. But where do those depressions come from? Maybe this is important for tropical depressions or monsoon depressions as well, which we don't really know where they come from. Or once you have an existing disturbance from an easterly wave or something like that, do these radiative feedbacks help it amplify and maintain itself? So, yeah, definitely there's still a bit of disconnect from the real world here, but I think we're sort of slowly moving our way to seeing how these aggregation mechanisms are important for reality.
So I have a quick question. So you showed some of the stuff with the rotating case where you turned off the Longwave and Shortwave feedbacks. Have you done the same thing in the non-rotating case?
Yes. In the non-rotating case, removing Longwave water vapor feedback completely prevents aggregation. Removing all the radiative feedbacks completely prevents aggregation. Removing the shortwave feedback only does not prevent aggregation. Removing the surface flux feedback prevents aggregation. Removing just the wind part of the surface flux feedback prevents aggregation. Removing just the disequilibrium part, the surface flux feedback does not. I just now finished a simulation removing the wind speed feedback from the rotating simulation. Haven't looked at it yet, but I'd be very surprised if it did not prevent the tropical cyclone from forming. But yeah, so I mean, again, the fact that removing these feedbacks in the non-rotating case completely kills aggregation, whereas in the rotating case, it doesn't kill it; it just very significantly delays it. Kind of, gets back at this point here that, the radiative feedbacks. I think I've provided evidence that they are important for the spontaneous tropical cyclogenesis, but they maybe are not as essential as they are for the non-rotating case.
Back on that real quick, then, if you go back a couple slides where you showed the evolution, and you said that they're quite similar between the cases, but time it takes in the rotating case for it to come. Maybe.
So it's.
I guess the axis is slightly different. But
It's slightly, not really.
It speeds up much quicker than non-rotating. So these
well,
feedbacks occur quicker.
Yeah, right away they do. I think, because going back to the movies, in the non-rotating movie, you saw that dry spot start to form right away. And then it took a really long time. It took, in fact, like 50 days for that dry spot to grow enough to get you that mature cluster. Whereas in the hurricane case, kind of nothing really happened for the first 10 days, and then once it started, it really took off quickly. So there is a time scale sort of difference on both ends going on here.
What would happen if you introduced the beta effect? Would it make any difference, do you think?
Well, I guess it would definitely cause the hurricane to drift. Right.
That would bring it over and might affect the vertical balance.
I'm not sure how you can really you can't put a beta effect, though, in a simulation like this that has doubly periodic boundary conditions and be dynamically consistent. Because it has to be, I don't have it. Anyway, it has to be the same, at the northern boundary and the southern boundary. Everything has to match up. So if your Coriolis acceleration is different, you're going to have all these like unphysical sort of things going on. If you have instead a bigger domain where you have, say, walls at the top and bottom, you could put in the beta effect and see what happens there.
You can put a background wind, right?
Yes, you could do that.
So what will happen? You just put a simple new wind where that's not good?
I haven't done that in the rotating case. In the non-rotating case, if you put in a mean wind, if it's strong enough, say more than 10 or 15 meters per second, it really weakens and delays, potentially prevents the aggregation. If it's a weak mean wind, like 2 to 5 meters per second, it still aggregates, and then it just advects it around again and again and again.
So they still get organized.
It still gets organized. But what happens when you put in a mean wind is you're reducing the effectiveness of the wishy feedback, because instead of, if you have the same sort of a constant wind everywhere added on top to your sort of gustiness, perturbations, they're not going to, you're not going to have as big a difference between the wind speeds in the dry regions and the moist regions. So you're reducing the amplitude of that surface flux feedback. And so that's why if you have a strong enough mean wind, it's harder for the aggregation to form. Yeah.
Yeah, I mean,
Just a quick question. So, if the MJO is considered as the self-aggregation, is it possible to explain why MJO was formed in the
I don't know. It's a good question. I mean, the sort of Indo-Pacific warm pool is where you have the warmest sea surface temperatures, and so to the extent that some of these feedbacks, particularly the long-wave radiative one, is temperature dependent. So, for instance, the long-wave clear sky radiative feedback is stronger positive feedback at higher temperatures, and so perhaps it's more favorable there. I mean, also just the fact that I don't know, any place that sort of is predisposed to have more convection to begin with, I think, then you're already kind of starting this process off. But yeah, that's a good question. Right. Yeah. There it is.
All right. So with that, let's thank Allison one more time for running the lunch.
Thank you.